All right, so we are very happy to have Mitali Bafna with us here today, joining remotely. So Mitali is a postdoc at MIT. She did her PhD at Harvard. She has been thinking about some very deeply technical topics over the last several years. So for instance, she has played unique games over all kinds of graphs, all kinds of constraint graphs coming from high dimensional expanders, like hyperconductive graphs, you name it. And she has developed quite a keen insight into high dimensional expanders, and she used that insight to give efficient construction for PCPs, which received the stock best paper this year. So that's what she'll be telling us about today. So over to you, Mitali. Thank you very much for coming.
Thank you so much, Akash. So today I'll be talking about this joint work with Dor Minzer, Nikhil Vyas, and Ziwei Yun. And this builds on our previous works and also which were concurrently also shown by works of Dixtin, Dinur, and Lobotsky. And I've actually prepared a shorter talk, so please feel free to stop me with questions. Okay, so let's start with what is a PCP. So suppose someone wants to prove a claim to you, and the claim you can think of as anything, for instance, the Riemann hypothesis. So one way they can do that is to give you a proof. And one way you check the proof is to just go through it line by line and check whether each line follows from all the previous lines. But instead of this long checking, a PCP gives you a way to encode this proof into a different format where you as a verifier can query just constant number of locations, toss a bunch of coins, then query constant number of locations and read constant number of bits in each location and verify whether they satisfy some constraint or not. And the guarantee of the PCP is that you will always accept correct proofs with probability 1, and you'll accept wrong proofs with all but some small probability of error. And in fact, if the claim is false, then no matter what proof a cheating prover gives you, like it could deviate arbitrarily from this encoding that it's supposed to give you, you will still accept with only small probability of error. So this is amazing because a priori something that would have taken you a long time that requires linear in the length of the proof will now only take you constant time, as long as you're okay with this probability of error. So ideally, we would like there to be no overhead in the size of the new proof, and also the error to be zero or very close to zero. And these improvements to these parameters of size and error also lead to improvements in downstream applications of PCPs that I will soon talk about. And today, our work focuses on the setting of PCPs where you're only allowed to make 2 queries to the proof, because this is the setting that is important for hardness of getting implications to hardness of approximation. So today, let's focus on this setting. And in this setting, let me tell you about what was the size versus error trade-off that was known previously. So the original PCP theorem, which gave the first such PCPs, showed that you can get polynomial size PCPs. So think of n as the original proof length. So you can get PCPs, an encoding which is polynomial in the original length, but with very large error. So some error which is close to 1. And so now the question is, can you bring down this error to 0? So one way to do that is to just repeat the verifier. Like the verifier can toss a few more coins and query 2 more locations and check again if there's some error. And querying in this way k times will give you error 0.99 to the k. But this increases the number of queries. So if we are only restricted to 2 query PCPs, it's not even clear that you can reduce the error. So this led to lot of, research into whether we can reduce the error, leading to a seminal work of Raz, who showed how to get down to any small constant error, but at the same time blowing up the size of the proof, again by some large polynomial factor. So this led to a lot of work to reduce the size of the PCP, like size of these PCPs, culminating in the work of Dinur, who showed how to get a mere polylog and blow up in the size, but again with large constant error. So a natural question that comes up is, can you simultaneously get a small size and small error? So Moshkowitz-Raz showed how to do this to get almost linear size and small error. And their PCPs were based on low degree testing. And on the other hand, there were also a bunch of barriers that were shown to extending the approaches of Dinur and Raz, like either improving the error of Dinur's PCP or the size of Raz's PCP. So our work overcomes these barriers by building a like new approach based on high dimensional expanders, which I will soon tell you more about. And there was a whole workshop last week on this. And these PCPs give like the following corollaries, which are pretty immediate based on all the machinery of hardness of approximation. So under the exponential time hypothesis, which says that deciding if 3-sat is satisfiable or not requires exponential time, you get that approximating 3-sat to a factor that's even slightly better than random takes 2 to the n by polylog n time. And you can get similar corollaries for solving linear systems. And also we show many more corollaries for even fixed parameter tractable algorithms, like finding k-sized leaks in graphs, or approximately finding. Okay, so any questions up till this point? Okay, so let me now tell you about some of the tools that go into our PCP construction. So firstly, let me describe how an equivalent view for PCPs, which is through CSPs or constraint satisfaction problems. So like switching to this view, I'll use this view in alt sometimes because this is more convenient. So let's think of the right-hand side as a constraint satisfaction. So firstly, let's think of the claim that the prover is trying to prove is just a 3-sat instance, whether this 3-sat is satisfiable or not. And on the right-hand side, because you have a 2-query PCP, this is the following 2 CSP that you can build. So put for each proof location, you put in a vertex in this graph. And each edge or each verifier tuple, so the 2 queries that the verifier makes is an edge in this graph. And on this edge, you can put in the constraint that the verifier is checking. And now the guarantee of the PCP theorem gives you that if the original instance is satisfiable, then the new instance that you create is going to be satisfiable, this 2 CSP. And if the original instance was unsatisfiable, then the value of the new instance, or like the number of constraints that any assignment can satisfy, is at most 0.99. Okay. Okay, so what we want to do is the following. So we want to start with 3-sat, and we can apply Dinur's PCP to get that to reduce to a 2 CSP with constant size alphabet, where in the yes case, when the 3-sat had value 1, you have value 1. And in the no case, you get that the value is at most 0.99, and the size of the 2 CSP, or the number of variables in it, is only blows up by a polylog factor. And what we want is to reduce it to another 2 CSP, where in the no case, the value goes down to 0. And but the size remains n polylog n. So first, let me describe this, how Dinur's reduction, like a high-level overview of Dinur's reduction, which used expander graphs. and then say something about how we can do the second step using high dimensional expanders. Okay, so let's recall what are expander graphs. So these are constant degree graphs, while at the same time having many of the connectivity properties that are possessed by a complete graph. So for instance, if you take any small set of vertices, it has a lot of edges going out of it. Okay, so why are expanders useful? So at a high level, the goal of a PCP is to take some proof which has one error and convert it or encode it into another proof that has many errors that are spread across the proof, so that the verifier can catch these errors with constant probability. Okay, so now let's take a CSP view of, let's say, the claim that a prover is trying to prove to you. Instead of a 3-sat instance, let's say that the claim for simplicity is that this expander graph is two colorable. So the CSP we are starting out with is, let's say, it's two coloring. And in the yes case, we want to reduce to another 2 CSP, which is satisfiable. And in the no case, we want to reduce to a CSP which is at most 0.99. So okay, so the one obvious proof that the prover can give you is just a green-blue assignment to the vertices. But let's say this violates only one edge, or the two coloring instance is not satisfiable. So instead, Dinu's proof says that instead of asking for just the assignment to vertices in the PCP proof, why not ask a larger assignment to every vertex? So you instead ask the prover to also give you an assignment to a small constant size neighborhood around that vertex. So now one edge that will be violated on the left is going to be, okay. So yeah, the verifier check will now be that you pick two locations which have some overlap. Let's say they overlap enough some vertices, and you check whether the prover has given you consistent assignment to other vertices in the overlap, and you also check whether all the edges are correctly colored in both the neighborhoods. Okay, and now the intuition is that one edge that was incorrectly colored is going to be part of many neighborhoods. And this expansion can be used to show that you can actually, the value of this 2 CSP on the right is going to be smaller than the value of the original 2 CSP. And if you keep repeating this procedure, you will finally get to a 2 CSP, which has value only value 0.99. So yeah, I kept on alternating between like a proof view and the CSP view. But I hope this is clear.
Yes.
Okay. Yeah. So so now the natural question is, can we use this approach to get down to value which is smaller than half, let's say, or does this approach get stuck at 0.99? And unfortunately, the answer is that this approach does get stuck at half, like cannot be used beyond half. And let's see why. So if you take a generic expander, locally, every neighborhood looks like a tree. Like imagine a random graph. Every neighborhood in random graphs will be like trees. So trees are too colorable. So what a prover can do is to totally ignore the original assignment and not encode it at all, but instead just give a random two coloring to every neighborhood. And now, even if a verifier would test consistency between two overlapping neighborhoods, let's say these neighborhoods which share an edge, uh, it will only catch the error of the cheating prover with probability half. So the issue is that, so basically, like the PCP error, you cannot hope to get it down below half for this expander graph coloring claim. So, and the issue seems to be that expanders are locally two colorable always, but globally they may or may not be two colorable. Okay, so this brings us to high dimensional expanders, and this is, I think, also the reason maybe that high dimensional expanders were proposed by Dinur and Kaufman to go beyond this barrier. So these are expanding hypergraphs. So on think of a universe of n vertices, but every edge, instead of containing two vertices, it contains a constant number of vertices. And again, they are supposed to sparsify the complete hypergraph or like possess many of the properties of complete hypergraph with, let's say, n to the k edges, hyper edges. But at the same time, they are supposed to have only theta of n hyper edges. Okay, and now we can see an immediate advantage over expander graphs. So let's consider the graph formed by this hypergraph where you replace every hyperedge with a clique. So now we are only looking at this the picture here as a regular graph. And now the neighborhoods in these vertex neighborhoods in this graph are no longer tree-like. They have many triangles and cliques. So so this kind of resolves this Bogdanov's barrier from the previous slide. So like suppose you had to prove this claim that this HDX graph is two colorable. Firstly, because it has many triangles, it can never be two colorable. So you can just ask the prover to give you an assignment to every triangle. And since triangles are not two colorable, the prover can never do that. So the PCP error is zero. So it seems like this graph that is not two colorable is witnessed by many not two colorable local parts. So there seems to be some kind of stronger local to global properties possessed by these graphs. But of course, like this is kind of a weird claim to prove because these CSPs, like two coloring, is not going to be have completeness ever. Like they, since you have triangles, you don't have like you can never be two colorable. So what about like other two CSPs on HDX graphs? Like what about three coloring? What would be the PCP error in this case? Or let's say like other two CSPs like 12 coloring or CSPs that don't have anything to do with coloring. Um, so it's not super clear whether like asking for, let's say, the assignment to every triangle would reduce the PCP error in these cases too. Okay, so that's really the question. Can we use these hypergraphs to reduce the PCP error for arbitrary 2 CSPs or arbitrary claims about HDX? So one challenge is that there are many definitions of expansion for HDX because every way to generalize the expander to higher dimensions leads to a different definition. So there seem to be like actually, let's say like, yeah, 3 to 4 definitions, and it's not clear which of them, if any, would imply this kind of error reduction for claims or 2 CSPs. And even if we could come up with a definition, the issue is that it's not clear you could have an HDX which satisfies this definition because random hypergraphs are not high dimensional expanders. So we have only 3 constructions based on algebra and topology. But nevertheless, actually high dimensional expanders do help to reduce the error beyond half. So what we showed is that if you take any 2 CSP on this HDX, so like take any constraints on the edges, and let's say the CSP has value 0.99, then you can build a new CSP where or let's say a PCP for it equivalently. where at every location is indexed by a hyperedge in the HDX graph. And you ask the prover to give you an assignment to every hyperedge. And the verifier checks whether all the constraints in the hyperedge are satisfied. So all the constraints in the clique corresponding to that hyperedge are satisfied. And also it queries two hyperedges with good intersection and checks whether the assignments are consistent on the intersection. So very similar to the Dinur's PCP. But now, because of hypergraph expansion, we can show that the value actually reduces to 0.01. And this overcomes this expander barrier of Bogdanov. And one interesting aside I won't talk about too much about is that these use like we had to build these objects in property testing called direct product tests and de-randomize like shorter versions of these. And actually, so it turns out that you can not just build a Bogdanov type counterexample, but a class of counterexamples. Even like you can even build some HDXs which won't work. Like just using spectral HDXs won't give you this error reduction. So there's a large class of counterexamples. And it turns out that you need a different notion of expansion, which comes from topology, and it's called coboundary expansion. And this is necessary as well as sufficient to reduce the error from 0.99 to 0.01. Yeah. And like here, just as an aside, if you know about HDXs, we use like this construction of HDX by Chapman and Lubbock. Okay. So any questions?
Yes, there is a question.
Okay.
I just have one confusion that you reduced 3 sat.
Oh, sorry. I could. Wait. I can't hear any.
I'll just give a better mic.
Oh.
Can you hear me?
Sorry.
Am I audible now?
Yeah.
I was just confused between when you said something like the 3 sat proof reduces to 2 colorability of CSP graph.
Oh,
So,
no, actually, that was just as an example. Like I was considering, instead of 3 sat, I was considering 2 coloring just to be more concrete.
but 3 sat is
It's not like 3 sat. No, so yeah, it doesn't reduce to 2 coloring, of course. But I was like, instead of starting with 3 sat, like to be more concrete, I was starting with, let's say, 2 coloring. Because if you want to build a PCP for 3 sat, you have to do it for 2 coloring. Like it's easier to explain the like the issue or the counter example using 2 coloring.
Oh, okay.
Yeah.
So, Mitali, I also want to understand one thing. So, I mean,
Yeah.
you said the spectral expansion for your HDXs does not suffice. On the other hand,
Yeah.
expansion is both necessary and sufficient. So, the question is, do you need both, or like, I mean, it's just item one as written?
Oh, yeah. Actually, so I think you need spectral too. Like otherwise, you should be able to build other simpler counter examples. I didn't fully verify, but like even to get this kind of direct product test, even in this 0.99 regime, I think you do need spectral expansion.
Okay, thank you.
Yeah. Okay. So yeah, somehow now I can't see the participants in my Zoom. It's weird. I'll just trying. Okay, anyway, I'll continue. Like maybe you could just interrupt me if there are questions. I can't see the participants. Um, okay. So So it seems like we have some gap amplification, like we wanted to reduce two CSPs from value 0.99 to value 0.01. This was the goal. So it seems like we almost have a PCP, but not fully, because what if the 2 CSP is not on a HDX graph? Like what if it's on an arbitrary graph? Because as someone already pointed out, you cannot even start with two, like, of course, you can't start with two coloring, but you can't really also start with two CSPs on HDX on particular graphs. Like you might have a 3-sat instance or an arbitrary 2 CSP, which is NP complete. So we don't really know if these specific 2 CSPs on structured graphs are NP complete or not. So what we do is to first reduce arbitrary 2 CSPs to 2 CSPs on HDX on these structured graphs using routing. So let me give you an outline of the whole reduction now. First, you can use Dinur's reduction to get from, I'll only talk about the no case, where if you have a 3-sat in the no case, then you get first to value 0.99, and you only blow up the number of variables by polylog n. Then in the next step, you can reduce arbitrary 2 CSPs to structured 2 CSPs, where the constraint graph, the constraints lie on this HDX graph that we had in the previous slide. And in the process, like the alphabet of the 2 CSP blows up, but let's ignore that for a moment. This we achieve by this fault-tolerant routing algorithms, which now I will talk more about. And then in the second step, now once we have these structured 2 CSPs, we can use this direct product testing that I just told you about to reduce value from value 0.99 to value 0.01. And finally, like we use known techniques in PCPs to reduce large alphabet down to constant alphabet. And each step in this reduction only blows up the size by polylog n. Okay. So now let me tell you about the first arrow, like the first blue arrow, because that's more more easier to explain than the direct product testing. And that also uses HD. Okay, so this is somewhat of it's like a almost new beginning to the talk. So yeah. And at the end of this section, I'll also tell you how it's connected back to PCPs, like how we can use these fault-tolerant networks from HDXs to like reduce CSPs, arbitrary CSPs to CSPs on HDX graphs. Okay, so we arrived at this problem through PCPs, but it was originally proposed by Dwork et al. And their motivation actually came from distributed computing. So let me tell you the problem at a high level, the problem that they proposed. So the question is to design, let's say you have n nodes who want to communicate to each other, but the question is to design a sparse network on these n vertices. Think of sparse as being constant degree ideally, and routing protocols between every pair of vertices, which may not be connected by an edge. So routing protocol is like just a protocol to transmit a message, let's say between this pair of vertices that I've highlighted. And it's an algorithm that only uses edges of the network. So for instance, one protocol might just be to transfer messages along a path in this graph. But you can also use other protocols, for instance, transfer along many paths in the graph and take a majority. So you can design any such protocols between all pairs such that each protocol is efficient. So each protocol should not use, many, many steps. For instance, here, let's say this protocol uses 4 steps. And together, the protocols are fault tolerant. So what this means is that if some constant fraction of the vertices behaved adversarially, for instance, they changed the message that they are supposed to send in a protocol, or so whatever they do, only some few constant fraction of protocols fail. Everything else succeeds in message transmission. So for instance, like if you did this path as a protocol, if the middle vertex just drops the message, then the whole protocol fails to transmit. Okay, so I will talk more about this model of like this problem soon, if it's not like if the model is not fully clear. So this was previously studied by Dwork et al. And also by other works after that using expander graphs. And they couldn't get like all the parameters of, let's say, constant sparsity and efficient, by efficient we mean like polylog and efficient protocols and constant fault tolerance, but we can use high dimensional expanders to solve this problem. So, and today for simplicity, let's fix some permutation. So let's say we don't want to design protocols between all pairs of vertices, but only want to design n protocols from one vertex, from vertex v to pi of v. So you have a fix a permutation on the n vertices. And like once you do this in a fault tolerant manner, you can lift it, like you can do it for the all pairs of vertices, also in fault tolerant manner. Okay, so let's see how to do this using expander graphs. So recall that these are constant degree graphs, so they're already very sparse, so that's good. So the question is, how do you get the protocols that are also fault tolerant? So firstly, between any two vertices, we have many paths of length log n. So the routing protocol you can do between vertex 1 and pi of 1 is to just send a message along this some path of length log n between these two vertices. So this is the first protocol, and then you can do this between vertex 2 and pi of 2 and so on. And you get n protocols. And additionally, you can design these paths using the property of expander graphs in a way such that at every time step, if you looked at all these protocols together, every vertex is used exactly once. So you might have heard of this. It's called low congestion networks, which have these properties. Okay. Or sorry, low congestion routing. So you don't use any vertex too many times. So let's see what is the fault tolerance this gives us. So suppose that now any 0.01 n by log n number of vertices are adversarially chosen to be faulty. So again, what this means is that, let's say one sends a message m to this vertex, the second vertex might just change the message it was supposed to send forward, and then the whole path, like if the second vertex on the first path was faulty, then the whole path might fail to send the required message. But if only 0.01 n by log n number of vertices are faulty, even if they are adversarially chosen after you design these paths, at most 0.01 n paths fail to transmit the required message. And this we can just show by union bound. So let me just pictorially show it. So first, only 0.01 n by log n number of paths fail due to containing a faulty vertex in the first time step. And the same thing might happen due to the second time step and so on. But there are only log n length paths. So overall, only 0.01 n paths fail. Okay. So any questions? Okay. So the natural thing you can ask is that can you support tolerance against constant fraction of faulty vertices? So this only supports tolerance against little of one fraction. And actually, the answer is that adversary could actually choose n over log n number of vertices to be faulty, and then all the protocols would fail. And this is actually, they can just do this by even randomly choosing n over log n number of vertices to be faulty. Okay, so the natural idea you might have is to add robustness to the routing protocols. So here, even if one vertex on this path fails, the whole path fails. So what if you could send a message using multiple vertices at every step? So let's say one sent a message to a small clique of vertices, and then the small clique of vertices sent the same message or the message they received to another second small clique. Every vertex in the second clique took a majority of all the messages it received, and then passed it forward in this way. And finally, the vertex pi of 1 takes a majority of all the messages it received to um, to get the received message. So now you can just observe that there can be many faulty vertices on the path, but as long as every clique in this path or every bubble here has at most half fraction faulty vertices, then the message transmission is successful. So now you might think that, of course, we don't have cliques in our expander graph. So how would you even do such a routing protocol? Because recall that we only can use edges of our graph. So one way you can try is to, add cliques to your expander graph. So finally, this won't end up working, but this motivates why you would think of HDX using high dimensional expanders in the first place. Okay, so let's try one simple attempt, which is to just replace every vertex with a clique and every edge in this graph with a biclique. So this is the graph you would get. And the routing you would try on this graph is just like every path on the left uh, is replaced by like a path on these cliques, like because every vertex corresponds to a clique, and every edge is replaced by this biclique, and like now the message transmission happens using majority votes. And actually, the same analysis, but like with the Chernoff bound, would just give you that these protocols are now tolerant to constant fraction of random faults. Because if you randomly chose constant fraction of vertices, like let's say 0.01 fraction of vertices to be faulty, with high probability, if each clique was, let's say, of size log n, um, with high probability, only 1 by polylog or 1 by log square n fraction of the cliques would be faulty. And then, the probability of having a faulty clique on the path, since the paths are of length log n, is very small. So most messages will succeed. So this was like fast, but yeah, basically using a Chernoff bound and just the previous argument, you get that this network is tolerant to constant fraction of random faults. Okay, any questions about that? Okay. Yeah, so of course, this is great, but you can easily see that this won't be tolerant to adversarial faults. So the reason is that the adversary on this network can just simulate the expander adversary, really, because we haven't done anything really non-trivial. So what the adversary on this network could do is to just simulate the expander adversary, whenever the expander adversary corrupts some vertex, it can corrupt the corresponding clique. And if there's a direct like one-to-one correspondence between the fraction of vertices corrupted and fraction of cliques corrupted, right? So you can just corrupt again only 1 by log n fraction of the vertices, which would corrupt like 1 by log n fraction of the cliques, and all the paths would again fail. Yeah, so again, you're not tolerant to constant fraction of faulty vertices if they were chosen adversary. And really, the issue is that these cliques are disjoint. So if you corrupt 1 by log n fraction faulty vertices, they directly correspond to like corrupting 1 by log n cliques, fraction of cliques. So if really we had many overlapping cliques, it's like conceivable that this is not possible to do. Like whenever you corrupt constant fraction vertices, let's say very, very few of the cliques get corrupted because there are, let's say, many more cliques than vertices. Okay, so this brings us to HDX, which gives you this exact structure that you need. So again, we replace every hyperedge with a clique to get this graph. And this graph has the property that if these cliques are large enough, and even an adversary chooses at most 0.01 n vertices to be faulty, then very, very few cliques, like let's say 1 by log square n cliques, have greater than half fraction faulty vertices. In some sense, this is like a Chernoff bound, but against adversarially chosen faults, and also for this, structured graph. So yeah, this is like a Chernoff bound for high dimensional expanders that was proven by Lichtenstein and Hopkins. So recall that this is only true for random faults in the expander plus clique network. And this again immediately gives you the fault tolerance that you would need. So firstly, you can set up these paths on the HDX where you can transfer a message from clique to clique using majority votes, and the paths are of length log n. And if these cliques are large enough and an adversary chose constant fraction of vertices to be faulty, then you can just use the Chernoff bound on the previous slide, and the same kind of argument that very few cliques are faulty in every step to show that only very small number of paths fail. Okay, so any questions?
There is a question, just one moment.
Okay.
How large are these cliques?
Yeah, so these cliques are of size log n for this, or at least log n for this argument to work.
Okay, thank you.
Yeah, I initially said the HDX is of constant, constant sized hyperedges. But yeah, in this argument, you would need log n sized hyperedge. Okay, so let me continue. Okay, so this gives you basically it gives you efficient protocols and fault tolerance, but turns out that these protocols are not as efficient as we would have liked. Like every vertex actually gets involved in 2 to the poly log n paths, like when you work out all the parameters of the HDX. So, but we can use similar ideas and like slightly more complicated protocols to actually get that HDXs support efficient routing protocols where each vertex is only involved in sends and receives polylog n messages throughout all the protocols, like throughout all the n protocols. And these protocols are tolerant to constant fraction of faults. So that if you corrupt constant fraction of vertices or even edges, actually, only small constant fraction of paths fail. And actually, these HDXs would give you like degree polylog graphs, but you can repeat, compose these networks with themselves to get down to constant degree graphs with efficient and fault tolerant protocols. So in this way, you can resolve the problem of Dwork et al. Using HDXs. So finally, let me tell you how this is all connected to PCPs. So let's just again, for simplicity, imagine that you have this two coloring CSP on this expander graph. But to do error reduction or value reduction, we want to first reduce it to a 2 CSP, which is very structured, and the constraints only lie on the green edges, like not on arbitrary edges. And imagine that the number of vertices on the left and the right is the same. So on the left, the verifier would have queried a random edge in the graph, but let's say the edge ij. But this edge, so label the vertices on the right, and ij may not be an edge in this green graph. So maybe ik and kj are edges. So instead of directly querying this edge, you ask the prover or like the new CSP, like let's think of it as a PCP prover. You ask the prover to give you more information in every location. So you basically ask it to give you a routing of i's label to j. So in the sense that you ask the prover to give you at the vertex, let's say the routing protocol was just sending message from I to j using the path ik and kj. Then you ask the prover at vertex I to give you i's label, at vertex k to also give you i's label, and vertex j would also be i's label. So basically all the messages that I, k, and j receive throughout this routing protocol, and in fact throughout any such routing protocol. So now the verifier would, query edges of these green edges to just verify whether the routing has been performed correctly. Like the label that K received is the same as the label that I sent, which you can verify only by looking at I and like the value of, the assignment of I and the assignment of K. And using the fault tolerance of all these routing protocols, you can show that if the initial CSP had value 0.99, then the new CSP you form in this way, like using these kind of constraints that verify routing, also has value 0.99. Yeah, so this value preservation is, you get this because of the fault tolerance. So now finally we have this 2 CSP, which, so this actually firstly shows that, approximating 2 CSPs on these structured graphs, like they are even more structured than expander graphs, is NP hard. Of course, the alphabet size is going to be very large here. Like the alphabet size is 2 to the polylog n, or it contains, each location here contains polylog n bits. So that's one consequence. And now once you have a 2 CSP on an HDX graph with value 0.99, what I showed you previously, like these de-randomized direct product tests can be used to reduce the value down to 0.01. Finally, as I said earlier, then you can perform alphabet reduction once you have the small value. So any questions to this?
I'm just curious, like it looks like
Yeah.
that this technique, the alphabet blow up size that it produces is kind of inherent. So if I want to go below 2 to the polylog n alphabet size, perhaps we have to use a different approach.
Yeah, so actually that's a great question. So there are a lot of algorithms for 2 CSPs on expanders, right? Like Barak, Raghavendra, Steurer. I think it's a good question that actually what is tight? Is the hardness tight, or so these are also expander graphs. So is it can we improve the algorithms or the hardness? So I actually don't know what you should expect. Yeah, so this technique would give you alphabet size, which is large, but maybe I don't know if it's tight or not.
All right. Thank you.
Yeah. But yeah, there's a large gap. Like if you looked at BRS algorithms versus the alpha, I think they can only handle they get polynomial time algorithms for approximating these two CSPs on expanders. But with alphabet, probably even just log n, or yeah, maybe even smaller than that. Okay, so yeah. Yeah, so that's all I had to say today. Thanks.
Everyone for the wonderful talk.
Thank you.
Questions for Mitali? There is a question.
So this is actually about one of the tools that you mentioned. So the Chernow bound for HDX is, so which kind of HDX definition does it use again? So like, does it require both spectral and yeah?
Yeah. So actually, that's a good point. The fault tolerance part, or even this Chernow bound, only requires spectral definitions.
Is there so because unlike the expander case, these are different. Is there a possibility that there might be a better Chernow bond if one uses spectral plus co-boundary or something?
I would think no. Like actually, there are like it's tight basically. Yeah, it's tight kind of because of trivial reasons.
Okay.
Yeah, co-boundary seems to be like a different, like kind of orthogonal to spectral
Okay.
expansion. Yeah.
More questions? Yes, there is a question.
Hello. Yeah.
Yeah.
So I want to question, how is this network actually, the messages are transmitted? The first person is transmitting the message to a click, and then in the click, everyone is talking to themselves and taking majority vote, and then transmitting
So
that.
yeah, you don't need that. Like you can each person is connected to the second click, and they can just send whatever they receive to every vertex in the second click. And now each vertex in second click will receive many messages. So it just takes majority.
Okay, so each person is
yeah.
just taking majority of the previous messages that receives.
Yeah.
Okay.
Yeah. And then broadcasting that. Yeah.
Right. Any more questions? All right. So let's thank Mitali for teaching us this stuff at 9:30 in the night.
Thank you so
Very much,
much.
Mitali. Thank you.
Okay. Bye.
Bye.